Hello everyone, we have been discussing the interpretation of suction control direct shear test data using extended M-C criterion. So let us discuss how to interpret the suction control triaxial test data using extended M-C criterion in this lecture. So in triaxial test setup, which is suction controlled, here we independently control UA, UW, so therefore you can control the suction and you can also control the all round pressure and the deviatic stress. So then you apply the deviatic stress so that you get the shear failure and you get the deviatic stress at failure and pore water pressure, etc. Then you can strength of the soil at different suction values using extended M-C criterion. So let us solve one simple problem. So here we have some synthetic data, that is data representative of extended triaxial tests, suction control triaxial tests. So you have series of tests conducted, say test 1 consists of UA minus UW, so where the suction is maintained to be 0 kilopascal. So essentially the test is conducted at fully saturated state, and the all round pressure, so that is sigma 2 minus UA, which is nothing but which is equals to sigma 3 minus UA, because this is radially applied in triaxial setup, so which is equals to 10 kilopascal, and then the failure of the soil took place when the major principal stress value of 60 kilopascal. Similarly, another test is conducted, test 2. Here the test is again conducted at saturated state, U minus UW is equals to 0 kilopascal, and similarly the sigma 2 and sigma 3 or sigma 2 minus UA and sigma 3 minus UA both are increased. So then the failure took place when sigma minus 1 sigma minus UA of 100 kilopascal. So this is one set of data conducted at saturation state, so that you can obtain C and phi values. Another set of test data conducted, say test 3, where UA minus UW is maintained to be 60 kilopascal, and sigma 2 minus UA and sigma 3 minus UA both are at 10 kilopascal. So this is similar to the first test, except that the suction value is non-zero, or it has some suction value. The test is conducted at unsaturated state. So obviously we expect that when the suction is increased, even though all round pressure is same, you expect to fail at higher load. So this would fail at 100 kilopascal. Similarly, another test is conducted, test 4, where the suction is maintained to be constant 60 kilopascal, but the all round pressure is changed to same value as test 2, so that is 30 kilopascal. So as the all round pressure is increased by keeping the suction value constant, then definitely the sigma 1 minus UA increases. So this value becomes 142 kilopascal. So it failed at higher major principal stress. So higher deviatic stress, it failed. So this is another set of data. So from the first set of data, one can obtain the C value and phi value, and from this data again you get C1 dash, here C dash, and you get phi B. No, here again you get phi dash. So using these two test data, you can get phi B. So this is how we get. Let us understand how we can solve this problem. This also can be represented in a matrix form. The test results, one can be represented as sigma 1 minus UA and sigma 2 minus UA, sigma 3 minus UA. This is 0, this is 0, is equals to 60, 10, 10. So it can be represented in this manner also. This is the test 1. Either way, we can represent the data in either way. So now the extended M-C criterion given by Fredland et al. That is sigma 1 minus UA is equals to sigma 3 minus UA times tan square 45 plus 5 by 2 plus 2c dash tan 45 plus 5 dash by 2. Here this is C1 dash, this becomes C dash when matrix suction is 0. So this is the expression we use for saturated soils also. So when this is, when you have suction in the soils, when this is defined for unsaturated soils, this is C1 dash, where C1 dash is equals to C dash plus UA minus UW times tan phi B. Fine. Now first test data, we can substitute the values of sigma 1 minus UA, that becomes 60 kilopascal, and sigma 3 minus UA is 10 kilopascal, then tan square 45 plus phi dash by 2 plus 2c. Here anyways the UA minus UW is 0, so I substitute the value of 0, then C1 dash is nothing but C dash. So this is 2c dash tan 45 plus phi dash by 2. From the second test data, again we can write this one as solving these two equations, we get, if you subtract the first equation from the second equation, then we get phi value, phi dash value is nothing but 2 times tan inverse square root of 40 by 20 minus 45. Then this is equals to 19.47. So phi dash is 19.47. If we substitute this value in this, we get C dash is equals to 14.14 kilopascal. Of course, this can be substituted into the other equation also. Either way, you get the C dash, the cohesion intercept, which is 14.14. Similarly, we can use the other test data, test 3 data when we use. So we get 100 is equals to 10 tan square 45 plus 5 by 2 plus 2c 1 dash. Here you have an intercept because the suction value is non-zero. Tan 45 plus 5 dash by 2. Similarly, the fourth data here, this is 142, which is equals to 30 tan square 45 plus 5 dash by 2 plus 2c1 dash. This is the same c1 dash because at the same suction value the tests are conducted, plus 5 dash by 2. When this is solved, you get this expression. So when you solve for 5 dash is 20.7 degrees, and when you substitute either of these equations, then you get C1 dash, which is equals to 27.8 kilopascal. So if you observe, if you notice the 5 dash value from the first two test data, you got 19.47. So from the last two test data you got 20.7. So when we take average value, so this is 19.47 plus 20.7 divided by 2. This gives a value of around 19.8 degrees, and C dash anyways we have 14.14. So we got two of the strength parameters estimated. We can estimate 5b dash by using those two expressions where the C1 dash is equals to C dash plus UA minus UW tan phi b. If we utilize this expression, C1 dash is known, that is 27.8. C dash is also known, that is 14.14 plus UA minus UW when the intercept is C1 dash is 60 kilopascal, that is into tan phi b. So when we solve this, we get phi b, which is nothing but 12.8 kilopascal. So phi b is less than phi dash in this case. So these three are the strength parameters of the extended M-C criterion given by Fredland et al. So this is how we interpret the triaxial test data, and then you can write the expression, that is tau f is equals to sigma minus UA f tan phi dash is 19.8 plus UA minus UW f tan phi b is 12.8 degrees plus C dash is 14.14. So this is a modified M-C criterion for this particular soil. So therefore at any given stress state, sigma minus UA and UA minus UW, the strength of the soil, shear strength of the soil can be estimated using this particular expression. So, the stress state of the soil is defined, then we understand the behavior. If the stress state changes with time due to some monsoon season, in monsoon season generally the water infiltrates into the ground or infiltrates into the soil slopes, then the suction values decrease. When these suction values decrease, how the strength changes can be evaluated using this particular expression. So, the same thing can be solved graphically, similar to what we did for direct shear test data. Let us examine how we do it. So, here in the extended M-C criterion, we have all the test data given. So, this is using test 1 and 2 data sets. This is at one particular UA minus UW, that is equals to UA minus UW is 0 kilopascal. So, the 3-dimensional diagram, that is a 3-dimensional surface, failure surface can be now approximated tau f, and this is sigma minus UA, and other axis is UA minus UW. So, this is a 3-dimensional thing we used to plot earlier. Now, because we are plotting at one particular UA minus UW, so you can now consider tau f here and sigma minus UA here, and this is at one particular UA minus UW, that is UA minus UW in this particular case is 0 kilopascal. So, as is 0 kilopascal, you can directly plot it here itself. This is 0 now, so directly you can plot it here. So, that is what we have done. The tau f or the shear stress on y axis and net normal stress sigma minus UA on x axis. So, when this is plotted, now we have two test data sets. So, two test data sets, one is sigma 1 minus UA, sigma minus UA is 60 kilopascal, this is 60 kilopascal, and sigma 2 minus UA and sigma 3 minus UA both are 10 kilopascal. So, this is 10. So, this is one more circle. This is one more circle, and similarly the other test data, that is sigma 1 minus UA is 100 kilopascal, and sigma 2 minus UA or sigma 3 minus UA is 30 kilopascal. So, this is second more circle. So, you draw a line joining these two circles. So, this is the line you get, and the angle of this line is phi dash, angle of internal friction. The intercept here is C dash itself, because UA minus UW is 0 here. So, the C1 dash is equals to C dash, that is 14.14 or 14 kilopascals. So, this graphically we can directly get this data. Second, using third and fourth test data, that is test data 3 and 4, we can obtain shear stress versus net normal stress by recognizing the values of sigma 1 minus UA and sigma 3 minus UA. Sigma 3 minus UA value is, for this particular data, that is test data 3, this is test data 3, test 3. Test 3 data, the sigma 3 minus UA data is 10 kilopascal, and this value is 100 kilopascal. Sigma 1 minus UA is 100 kilopascal. And similarly, the test 4, the sigma 3 minus UA is 30, and sigma 1 minus UA is 142 kilopascal. So, this is 140 and this is 142. So, now again we join a line to these two circles. So, this is a failure plane. So, this failure plane once it is drawn, the angle is, this is the angle of internal friction, that is 20.5 degrees, and the intercept is C1 dash, this is 27 kilopascal. So, now you got C1 dash and phi dash. Now you can take average value of phi dash. Earlier you got a 19.47 or 4, now 20.5. So, we take the average and we get the average value. Nearly 20 degrees we get. So, this can be represented in this particular manner. The first test data is this, test 1, and this is test 2, and this is test 3, and this is test 4. So, this test 1 and test 2 both are conducted at UA minus UW of 0. So, this is UA minus UW axis, the z axis. So, when UA minus UW is 0, on this axis this particular test data is conducted. So, tau f versus sigma minus UA at UA minus UW is equals to 0. So, this is the data. So, this is the failure plane, that is angle of internal friction is 19.5. Similarly, at UA minus UW value of 60 kilopascal, these tests are conducted. So, this is represented in this manner, and this line is the failure plane line, that is 20.5 degrees, and which is nearly parallel to this line, because the values are very close, right. Now, as we have the values of C1 dash equals to C dash from the first two test data, that are conducted at 0 kilopascal UA minus UW. So, the matrix suction 0, correspondingly the value of this one is 14 kilopascal. So, corresponding to matrix suction 0, the C1 value is C1 dash is equals to C1, that is 14 kilopascal, and corresponding to matrix suction 60, the C2 dash value is 27 kilopascal. So, another intercept. So, now if you join these two lines, you get phi b, that is 12.4 degrees. The intercept in fact is, anyways it is starting at matrix suction 0. So, you got C dash. So, therefore, C dash is estimated, which is 14 kilopascal, and phi dash is estimated, which is 20 degrees, and phi b is estimated, which is 12.4 degrees. This data which is obtained graphically is very close to the analytical technique. This data is very close to the data obtained from the analytical technique. Now, knowing these three parameters estimated, now you can draw the failure surface. So, the extended Moore M-C criterion gives a surface. So, this is the surface. The pink colored one is the surface, failure surface. So, here earlier data which we had drawn from the test 1 and test 2 and test 3 and test 4. So, this is estimated to be 19.5, which is phi dash, and this 20.5 is also phi dash. You can average it and give the value of phi dash as 20. So, you can in fact take phi dash as 20 in both the cases, but here it is as it is drawn. So, then here from here to here the intercept is 27.5 kilopascal from this point at 60 kilopascal UA minus UW. So, this is 27.5 kilopascal intercept, and here the intercept is 14 kilopascal. So, line joining these two with respect to the axis which is parallel to this one, matrix suction line, in between these two, the line which joins the two intercepts, and another line which is parallel to the matrix suction line, the angle made between these two lines is your phi b. So, that phi b is 12.4 degrees. So, for this surface, this angle is 20 degrees, that is phi dash, and this angle with respect to the the line parallel to UM-UW is phi b. So, once phi b is known and phi dash is known, we can draw the failure surface. So, this is the failure surface for the extended M-C criterion using track shell test data. Let us solve another problem. So, here the data is summarized in this manner. So, test data and UA minus UW, so which is controlled, and sigma 3 minus UA which is maintained, and sigma 1 minus UA which is observed. So, now test 1, the UA minus UW is maintained to be 40 and the sigma 3 minus UA is maintained to be 30, and this sigma 1 minus UA is observed to be 100. For test 2, this is again 40, UA minus UW is 40 and sigma 3 minus UA is 80. So, at higher all round pressure the test is conducted by maintaining the same matrix suction. Therefore, the sigma 1 minus UA should now increase. This value is 200. Then now the matrix suction is increased to 120 kilopascal, and sigma 3 minus UA is now 30. Then sigma minus UA should be higher than 100, which is observed to be 180. And the fourth test with the same matrix suction, but increasing the all round pressure to 80, the same value as the second test. Now this should be higher than 200 because the matrix suction is higher than the second case. So, this is 280. So, these are the observations. Here there is one interesting aspect, that is the reason why I am actually discussing this particular example. So, here no test is conducted at fully saturated state. In case of Bishop's effective stress, Bishop's extended M-C criterion, Bishop's modified Mohr-Coulomb criterion, to estimate C5 values and Xi-F, one needs to conduct the tests at fully saturated state. At least 2 tests should be conducted. If you have cohesion intercept also, then minimum 2 tests need to be conducted so that you can estimate cohesion and angle of internal friction. And when these 2 values are estimated, other tests can be conducted at higher matrix suction values so that you can obtain Xi-F value at corresponding matrix suction value. However, in this case, even though you have cohesion intercept, you do not need to conduct the tests at fully saturated state. Without knowing the test data at fully saturated state, you can obtain the entire Mohr-Coulomb failure, you can obtain the failure surface. Let us see how we obtain. So, briefly I discussed this using these 2 test data sets. Using these 2 test data sets, you can obtain C1 dash and phi dash, and using these 2 test data sets, you can obtain C2 dash and phi dash. So, using these two test datas, you should be able to get C dash and phi b. Let us see how we get. So, from the first two sets of data, we get, when we substitute in the M-C criterion, that is sigma 1 minus UA is equals to sigma 3 minus UA tan square 45 plus phi by 2 plus 2C1 dash tan 45 plus, this is at one particular UA minus UW. So, here when we substitute sigma 1 minus UA from the second test data, this is 200 is equals to 80 tan square 45 plus phi by 2 plus 2C1 dash tan 45 plus phi dash by 2. From the first test, this is 100 40 tan square 45 plus phi dash by 2 plus 2C2 dash, because this is conducted at one particular suction, which is not same as the suction value which is used in the first two test data. First test, sorry. Here this is C1 dash because this is conducted at the same suction. So, now when you simplify this is simply 100 and this is 40 tan square 45 plus phi dash by 2. If you solve for phi dash, you get phi dash is equals to 19.47 degrees, which is same value as we obtained in the previous case. So, you can obtain the C1 dash. C1 dash is equals to 14.15 kilopascal. Just in the previous cases, you can directly substitute phi dash value in one of these expressions. You can get C1 dash, which is 14.15 kilopascal. Similarly, this is 1 and this is 2. When you use, sorry, this is 2 and 1. So, this is 2 and this is 1, and similarly when you use 4, 280 is equals to 180 tan square 45 plus phi by 2 plus 2C2 dash, because these two are conducted at UA minus UW of 40 kilopascal and this one is 180 30, sorry, this is 30. So, this is 50. So, that is why this is half and you get the same value phi dash. So, here this is 30 tan square 45 plus phi dash by 2 plus 2C dash tan 45 plus phi dash by 2. These two are U minus UW of 120 kilopascal. This is fourth and this is third data. So, when we solve this, we get the same phi dash, which is 19.47 degrees, and C2 dash is 42.43 kilopascal. So, from the expression that C1 dash is equals to C dash plus UA minus UW times tan phi b, using this expression you can substitute C1 dash, that is 14.15 is equals to C dash plus UA minus UW is 40 tan phi b, and in the second expression C2 dash is 42.43 is equal to C dash plus 120 tan phi b. When you solve this, you get phi b is equal to 19.5 kilopascal, which is same as your phi. Phi is nearly same, and C is 0 kilopascal. So when the intercept, this is intercept is 0, that means this is sand. The test data is for sand. So you got phi dash, which is same as 19.45 or 5 degrees. Sorry, this is degrees. So you have phi dash, phi b dash, and C dash. All these three strength parameters could be estimated just by utilizing 4 test data sets. So these test data sets are essentially we obtained by maintaining one particular suction value. 2 test data sets could be obtained by changing the all round pressure, and another set of data can be obtained by maintaining different matrix suction but changing the all round pressure. So if we have such data, we can obtain all the strength parameters estimated. Quickly let us see how graphically this could be done. So here as we have done earlier, the net normal stress, that is sigma minus UA, and tau f are plotted. This is at one particular UA minus UW, that is UA minus UW is 40 kilopascal. So at 40 kilopascal, when we use the test data 1, this is for test data 1 and this is test data 2. Then we obtained the angle of internal friction, that is 19.5 degrees, and the intercept C1 dash, this is not equal to C dash because this test is conducted at one particular matrix suction value. So this is 14 kilopascal. Then the other 2 test data were used, where this is test data 3, test 3, and this is test 4. So the angle of internal friction is same, that is 19.5 degrees. This is C2 dash, which is not 14. Here we could see that this is 42. So these are around 42.5. So this is 42.5 kilopascal. So the angle of internal friction is, the angle of internal friction value is same for both the cases, but the intercept value changes from the first set of data and the second set of data because the matrix suction value changed. Now here this is 14 and this is not 27, this is C1 dash and this is C2 dash, this is 42.5 kilopascal, and here 19.5 and this is also 19.5. Sometimes the measurement errors would be there while plotting, and here this is the test data 1, 2, 3 and 4. So this is, if you observe, which is on an axis of this is the matrix suction axis. So this is at a value of 40 kilopascal. So this is 40 and this is 80, 120, 160. So here again at 120 So, that is another matrix suction value where the tests were conducted at 120. So, this is drawn. So, this is how now we locate the test data of all the 4 test data on the 3-axis plot. Now, once we have the phi dash, now phi dash and cohesion intercepts, the first intercept value 14.14 kilopascal or 14 kilopascal, which is obtained at matrix suction value of 40, and another intercept is obtained, that is 42.5 at 120 kilopascal. So, when these two test data are plotted on tau f versus matrix suction plot, so when you draw the straight line joining these 2 points, the line passes through origin. So, the cohesion intercept C dash is equals to 0, which is at matrix suction of 0. So, this we obtained for graphically. Now, the angle of the angle which indicates phi b is 19.5 degrees. So, this is how we get phi b estimated. Now, we have all the data phi dash, phi b and C dash. So, now this data, this line this line is with phi b, sorry, this line is with phi dash, this line with horizontal makes phi dash 19.5, and this line joining these 2 planes is phi b, that is also 19.5 for this particular case. In this particular case, the phi dash is equals to phi b. So, here this line joins from origin, and at 40 kilopascal of matrix suction, the intercept is 14, and at 120 kilopascal matrix suction, the intercept is 42.5, and this line with respect to horizontal line, with respect to the matrix suction line parallel to this angle is again phi b. In this case, phi b is equals to phi dash, therefore, this is 19.5, and this line is parallel to this line. These two are parallel, and again this and these two are parallel, and this is phi dash, and again this is phi dash. So, this represents a failure envelope which is a surface. So, this particular surface can be drawn due to the model given by Friedland et al. So, in summary, if we compare the modified M-C criterion which is given by Bishop and extended Moore-Coulomb criterion which is given by Friedland et al., there is a slight difference. Here the strength parameters are C dash, phi dash and xi f, which is a functional form, which is function of u minus uw. In the Friedland et al., the strength parameters are C dash, phi dash and phi b. So, these are the strength parameters in Bishop, and these are the strength parameters in Friedland et al. The tests, the triaxial tests or direct shear tests, we need to conduct these tests, to estimate these strength parameters. We require suction control direct shear test data or suction control triaxial test data in a specified manner. For example, in case of Bishop's model, we require the test data at UA minus UW is equal to 0, that is at fully saturated state. At fully saturated state, we require 2 sets of data minimum. Because from these 2 test data we can obtain C dash and phi dash. If you have sand, then anyways the cohesion intercept does not exist at saturated state, so 1 test data would be sufficient. And then you need to conduct series of tests, test 3, 4, like that, series of test data to obtain the values of xif. Xif in this case is 1, but other cases xif need to be estimated. Xif can be estimated using the expressions for different suction values. When you maintain different suction values in different tests, you can obtain xif value. Xif value changes from 1 at saturated state to nearly 0 at nearly dry state. In Friedland et al. Case, we do not require series of test data, we just require 4 test data. 2 test data should be conducted at one particular UA minus UW. 2 tests need to be conducted, test 1 and test 2. So in these 2 tests you can vary all round pressure sigma 3 minus UA if it is a triaxial test, or you can vary the net normal stress if it is a direct shear test, and conduct another two tests, test 3 and 4. Again by varying sigma 3 minus UA or net normal stress and direct shear, and conduct these 2 tests. So from this test you obtain the cohesion intercept, one particular cohesion intercept at UA minus UW and angle of internal friction, and from these 2 tests you get another cohesion intercept and angle of internal friction. So by solving these 2 expressions for cohesion intercepts, we get C dash, phi dash and phi b. By solving these 2 expressions for cohesion intercept, we get C dash and phi b. Anyways, we already got the phi dash, so we get all the strength parameters. We do not require to conduct even the tests at fully saturated state in case of Friedland et al. Model, that is extended M-C criterion. So this way we can obtain the strength parameters using modified M-C criterion and extended M-C criterion by conducting different set of tests under suction control, in suction controlled triaxial or suction controlled direct shear tests. Thank you.